In this video, I'm going to be going over special right triangles. And now what these are is they're right triangles where if you set the angles up other than the right angle in such a way, you get common ratios that apply throughout all the sides. And you can use these to solve for a lot of problems in trigonometry where you see these angles come up. And that doesn't make a lot of sense when you just explain it out, but let me show you with an example. And so there are two what you call special right triangles. And the first one is going to be the 45-45-90 triangle. And so you're just going to set up a right triangle here. And both of these angles are going to be equal to 45 degrees. And because it's a right triangle and these two angles are equal, then that means it's an isosceles triangle. And therefore, both of these sides are equal as well. And I'm going to go ahead and label these sides. I'm going to call this A, I'm going to call this B, I'm going to call the hypotenuse C. And so since these sides are equal to one another, then that means A and B exist in a 1-to-1 ratio. And now if you're to plug these values into the Pythagorean theorem, or these variables into the Pythagorean theorem, you get a squared plus b squared equals c squared. That's just the Pythagorean theorem right there. And since we know that a is equal to b, we can substitute one of these variables in for the other. I'm going to do a in this case into b, but you could do it either way since they're equal. And so you end up with a squared plus a squared equals c squared, or in other words, 2a squared equals c squared. And now if you're to square root this to get rid of these powers, you end up with root 2a equals c. So therefore, c equals root 2 times side length a, or side length b, since they're both equal to one another. And so for every triangle, every right triangle, where both of the sides are equal to 45 degrees, these ratios will hold constant, no matter the size of the triangle. And you can use these to solve for many problems in trigonometry, some of which we'll be going over in later videos. And so there's another special right triangle known as the 30-60-90 right triangle, which I'm going to go over now. And the proof for this one is a little bit more complicated, but nonetheless, it's still pretty easy to grasp, and it's going to lead us to a lot of insight in those later trigonometry problems. So, the first part of this proof is to set up an equilateral triangle, where all of these sides are equal to some side length. Let's call that length C. These are all side length C. And all of these angles are going to be 60 degrees, since they have to add up to 180. Alright, now what you're going to do is draw a line from this top point all the way down to the bottom side such that it bisects it. And now you have side C divided into two sides equal to 1/2 length C. Let's call that length B, where B equals 1/2 of C. Or in other words, C equals 2B. And now we already have one of the first components of our special triangles, where this side C is equal to 2 times this ratio B. Or in other words, they exist in a 2-to-1 ratio. So I'm going to go ahead and label that. I should also label these angles a bit better as well. This is 60 degrees. And since this one's been bisected up here, it's going to be 30 degrees. And so now what about this side length? Well, let's call it A to be consistent with the Pythagorean theorem. And if you actually write out the Pythagorean theorem for this problem, I'm just going to start off with the a squared plus b squared equals c squared. And since we know that c is equal to 2b, we can just plug that in. So you get a squared plus b squared equals 2b squared. And if you actually evaluate that out, that becomes 4b squared, since the power is distributed. And now, if you're to subtract b squared from both sides to isolate this a, you end up with a squared equals 3b squared. And now if you're to take the square root to remove the power, you end up with a equals root 3 times b. So a and b exist in a root 3 to 1 ratio. And that's how that is derived. And now, to finally summarize, I'm just going to write all the triangles out with their respective angles and ratios so you can get the full picture. So here we have the 45, 45, 90 triangle, where both these angles are equal to 45 degrees. And the ratios of their sides are 1 to 1 to root 2. Root 2 being the hypotenuse. And here we have the 30, 60, 90 triangle, where you have one side equal to 30 degrees, one angle equal to 60 degrees. I don't know why I put a square there, I meant to do the degree. And so their sides exist in ratio 1 to root 3 to 2. And so you want to be very careful not to mix these up on the 30, 60, 90. Remember that the 1 is always opposite the 30 degrees, since it's the smaller angle. And the root 3 is always opposite the 60 degrees. And this looks like a Z, so I'm going to try and curve it out a bit. Yeah, and so once we start getting into trigonometric ratios and the unit circle, these special triangles are going to yield us a lot of insight, and they're going to be very helpful for solving those trigonometry problems. Anyways, that's all for now. So thank you for staying with me thus far, and I hope you'll join me for the next video.